Okay, section 7 on inverse relations and functions. So first, we learned about the vertical line test at the beginning of the chapter to determine if a relation was a function or not. So if it passed the vertical line test, it was a function. Now, if we have a function that passes the horizontal line test, then that function has an inverse and is called 1 to 1. That means for every one x, there's exactly one y. So in example 1, I have the function x to the 5th power plus x to the 3rd power minus 1. And I'm going to put that equation into my calculator and graph it and determine if I can use the horizontal line test to see if it has an inverse. So here's the graph of this function. There's one spot on the function that looks a little fishy that kind of looks like it is a horizontal line, right at this section of the graph. So people might tend to think, oh, there's a horizontal line right there, so it would not pass the horizontal line test. But if you actually zoom in onto the graph, if you do zoom to enter, you're going to see that that's not actually a horizontal line. It does curve. It's just hard for the calculator to show it at such a tight spot. So this one does pass the horizontal line test, which means that it does have an inverse. Okay, so if a function has an inverse, then we want to be able to find the inverse. So here are the steps to find the inverse of a function. Step 1, use the horizontal line test to see if it's 1 to 1. Step 2, we're going to replace the f of x with y in the equation, and then we're going to swap the x's and y's. So everywhere there's an x in the equation, we're going to put a y. Everywhere that we had a y, we would put an x. Step 3 is to solve for the new y. Once you have done that, you're going to replace the y with f inverse of x. Then you want to look at the equation for this inverse function and determine, are there any values for which it would be undefined? And usually there's 3 cases that we're looking at. So first, a polynomial function could be like that example 1, x to the 5th power, etc. That's a polynomial function. Well, its domain is all real numbers. But when you have a reciprocal function or a radical function, that's when we have some exceptions. So for a reciprocal function, like 1 over x, it's going to be all real numbers except whatever will make the denominator equal to 0. So you set the denominator equal to 0 and solve for x. That will give you the values where it is undefined. The other option is a radical function, so if it has a square root in it, then that's going to be all reals also, except whatever will make the underneath the radical become imaginary. So you usually set whatever is underneath the radical greater than or equal to 0 and solve that inequality. That will give you what your domain should be. So let's look at some examples of finding the inverse of a function. Example 2, I have f of x equals x divided by 2x minus 1. So here's the graph of this function. First, we want to use the horizontal line test to determine if it has an inverse. So looking at this function, some people might think that it may not have an inverse because there's spots right in here where it looks like it could be a horizontal line. But if you think about it, the further left this graph goes, the further up it's going to go ever so slightly. And same thing on this other side. The further right it's going to go down ever so slightly. And it's going to get closer and closer to those asymptotes. Okay? So those would not justify that it would fail the horizontal line test. This will be okay on this one. So we're going to find the inverse. So I'm going to start by writing y equals x over 2x minus 1. Then we're going to switch the x's and the y's. So everywhere I have an x, I'm going to put a y. Everywhere there's a y, I'm going to put an x. So now I'm going to solve this new equation for y. I need to get y by itself. So I can see that on the right-hand side, it is being divided by 2y minus 1. So to get rid of that or move it, I need to multiply both sides by 2y minus 1. So that's going to leave me with x times 2y minus 1 equals y. So I'm going to go ahead and distribute the x on the left-hand side. So this will be 2xy minus x equals y. Okay, I want to move and get anything that has a y on the left-hand side and anything with an x or without a y on the other side. So I'm basically going to switch places of the minus x and the y on the right, because I would subtract y and add x, so they wind up switching places. So now I have 2xy minus y equals x. I notice that the two terms on the left both have a y in common, so I'm going to factor the y out. When I factor the y out, I'll be left with y times 2x minus 1 equals x. Again, the goal is to get y by itself, so I'm going to divide by 2x minus 1. So y equals x over 2x minus 1. Since y is by itself now, we replace y with f inverse of x. Now you're probably thinking, well, that was silly. We did all this work and we had the same exact equation we started with. Total coincidence on this equation that the function and its inverse are the exact same function. Okay, so this doesn't happen all the time. It does happen occasionally, but the original function and the inverse are the exact same. Okay, now we want to talk about the domain of this function. So this is a rational function. The domain is going to be all reals except whatever will make the denominator equal to 0. So I'm going to set the denominator equal to 0 and solve. So I would add 1 and divide by 2, and this would be x equals 1/2. So this means if I plugged 1/2 into this function, it would make the denominator 0 or undefined, so that cannot be part of the domain. So all reals except x equals 1/2 is the domain of this function. Okay, now we're going to do the same thing for this function, 2 square root times, or square root of x minus 1. So if I graph this function, it looks like this. And I want to use the horizontal line test to determine if it passes or fails, to see if it has an inverse. And this one does pass the horizontal line test. So we can move forward in finding the inverse. So I'm going to write y equals 2 times the square root of x minus 1. I'm going to switch the x and y's. And now my job is to solve for the new y. So I'm going to divide both sides by 2. To get rid of the square root on the right, I need to square both sides. So this is going to be x over 2 all squared equals y minus 1. When I square x over 2, that's going to be x squared over 4. Now I can just add the 1 that's on the other side. So x squared plus over 4 plus 1 equals y. Since y is by itself, we're going to replace y with f inverse of x. So f inverse of x equals x squared over 4 plus 1. Okay, this time, if I look at this function, this is actually a polynomial function. There's no variables in the denominator and no square root of a variable. So this time, the domain is all real numbers. Okay, so now that we know how to find the inverse of a function, we want to be able to determine if two functions are inverses of each other. And this is only true when you plug in the two functions into each other if they simplify and equal x. So f of g of x is going to simplify and equal x, and g of f of x will simplify and equal x. Okay, so we're going to have to check both of those to make sure they simplify to x. The reason they both equal x is because they would be symmetric across the line y equals x on the graph. Okay, so I have two functions, f of x equals 2/3 x plus 2, and g of x equals 3/2 times x minus 2. So I'm going to use my color coding again, and I want to plug one function into the other and see if it simplifies to equal x. We're going to have to do both g of f and f of g. So for f of g, I'm going to plug the g function into the f function. So this is going to be 2/3 times 3 halves times x minus 2 plus 2. Okay, so I need to simplify as much as possible. Out in front, 2/3 times 3 halves will actually cancel those numbers out, and I'll be left with x minus 2 plus 2. And then the minus 2 and plus 2 are going to cancel each other out, and I'll be left with x. So this is good. F of g equals x. Now I can't just stop here. I have to check the other function as well. So g of f of x, this time I'm going to plug the f function into the g function. So 3 halves times 2/3 x plus 2 minus 2. So we can see that inside the parenthesis, the plus 2 and the minus 2 will actually cancel each other out. So I'll have 3 halves times 2/3 x. And then 3 halves times 2/3. Again, those cancel each other out, and we're left with x. So since both f of g and g of f simplified to equal x, these are inverses of each other.